Combining these two formulas gives us this formula. Not rocket science here. We're just setting the two left-hand sides are the same, so we set the two right-hand sides equal to the same. We continue, we play around with the math a little bit, and we get this very simple formula, that 1 over the magnitude of z prime plus 1 over the magnitude of z equals 1 over f. That's the thin lens equation, and any points that satisfy that equation are in focus. Okay, so if my film plane on a thin lens assumption or a thin lens model, if my film plane is z prime away from the lens for a focal length f, then everything that is z away will be in focus. So by moving the lens in and out a little bit from my film plane, I change where in the world things are in focus. So I can change the z prime easily. I can move the lens in and out from where my film plane is, and that changes the points out in the world that are in focus. There's a cool little thin lens app. Took me 4 times to say that before I got it right. It's posted here on the web, and it just lets you sort of play around with how you change the geometry of what's going to happen.
Let's try and apply this equation to bring an object into focus. Here's our lens and image plane. Now say we have an object point P that gets projected onto the image plane at point P prime. Now let's complete the thin lens diagram. We know that rays of light from P that are parallel to the principal axis, after refraction, cross the principal axis at a point that is focal length away. So that distance is f. Similarly on the other side, that is also f. The distance of the object from the lens is z, and the distance between the image plane and the lens is z prime. Let's say the focal length f is 50 millimeters. Now consider 2 scenarios. One where the object is 1 meter away, and second where the object is 2 meters away. At what corresponding values of z prime would the object be in focus? Enter your answers in the boxes provided in millimeters with up to 2 decimal places of precision. As you might have guessed, we want to apply the thin lens equation. Let's make our units consistent by converting z1 to millimeters. Now applying the formula, we know that 1 by z1 prime plus 1 by z1 is equal to 1 by focal length. Solving this for z1 prime gives us 52.63 millimeters. Similarly for z2 prime, we have 51.28.
One of the cool things about real lenses is, as I'm looking at a scene, if I want to, I can just change a little bit the focus in and out. Now, for those of us who use cameras that just take pictures, our goal is to put something in focus or out of focus, etc., whatever. If you're like Megan, who thinks static pictures are like just way old school and the only thing that matters is video, then the idea of changing focus during video is interesting. Generates something, it's called pulling focus or a focus pull, and you get this really cool effect. And here you can see this picture of this, pretty sure that's the water temple in San Francisco. Somebody else might remember. And there's the back end, that's the polite way of saying it, is of a duck. But you can kind of see that it's shot through a fence, and as I run the video you can see how changing focus changes how far in the scene, how far Z has to be in order for it to be in focus on the image plane. And that's pretty cool. One of the important things when you talk about real lenses is, for the photographers among you, you know about this. For those of you who are new to it, it's cool. It's called depth of field. And depth of field looks at the question of, okay, I've got some depth in space that's exactly in focus. How much does focus change as we get a little bit off of that distance, right? So if I move a little bit off of the point that's precisely in focus, how much does the focus change? And what that's controlled by actually is the aperture. And the reason is, you can see here, so here we have a wide aperture. And with a wide aperture, these rays diverge quite a bit. If my film plane, instead of being here, okay, was actually here, okay, the rays from this point would have been spread out a lot, so it would have been out of focus a lot. But on this smaller aperture, okay, where things were supposed to be in focus here, if I actually am off by a little bit there, that is, that my film plane has moved a little bit, you see that the spread is much less. And that's why the depth of field is much better. That's illustrated here. These are some pictures from Wikipedia. So here's a picture of a flower. You'll notice the flower itself is beautiful and sharp, and the background is totally out of focus. Now, it says f/5.6. Now, this is f for aperture, not f for focal length. I apologize, those of you who buy lenses, you'll buy a 50 millimeter lens, f1.4. The f is about the aperture. It means the smallest aperture, the largest aperture it can get. Also, f's are inverted. The bigger the number, the tighter the value. So 5.6 is a relatively larger aperture compared to, say, f32. So here, same flower taken from the same position, but you'll notice now that the background is in sharp focus. So if you're a photographer and you want to separate out your foreground from your background, you want to have a wide open aperture. If you're trying to look at a landscape and you want to see everything in focus, you want a very tight aperture. Here's a very nice example of depth of field. The focal plane obviously is somewhere in the middle of the phone, so the stuff that's in front and the stuff that's in back is out of focus. Another property of our imaging systems is field of view, sometimes called zoom, which is probably not quite right, but it's this idea of how wide of a view do we have. And I'm going to show you this in a lens that can change its focal length to show you that the field of view is a function of the focal length. There are lenses that can change their field of view while staying in constant focus are called zoom lenses. There are some lenses that you can change their focal length, but you have to refocus. Those are actually called variable focal length lenses. That's just the nomenclature. Here we start off with a very wide angle shot. It says 17 millimeters. And you see this little circle up there that's on that boat? As we step through and we increase from 17 millimeter to 28, to 50 to 85, what we're doing is we're increasing the focal length of the lens. Here we are at 135, 300, 500, and that's 1,000 millimeters. So we've gone from a focal length of 17 millimeters to 1,000 millimeters. That's a ratio of greater than 50 to 1. And there's that guy on the boat, right? Same boat back here. All right, there he is. Okay, so that's incredible zooming. So you think they used a tripod? Well, of course they did, right? In fact, this is something you might think about if you haven't thought, right? Let's assume for a moment that your hands shake just a little and they cause a small amount of angular deflection. Well, if my image is looking at something this wide, then a small amount of angular deflection doesn't move my pixels very much. But suppose my angle of view is, a degree or just a couple degrees, well then a small amount of angular shift of my hands is going to move the pixels a lot. And that's why the longer the focal length, the more you have to stabilize your image, and that's why for really nice zoomed out lenses you have to have a tripod. It's not just because they're heavy, it's because you need to have things be perfectly still. Now we can compute the field of view, and the field of view actually depends upon two things. One we already know, right? We know that it depends upon the focal length, but it's also going to be a function of sort of how big is the light sensitive element. So here, calling D the size of the retina, okay? So the retina is the thing in the back of your eye that's sensitive to light. Just think of it as the light sensitive medium. So D is this whole size, okay? Here's F, our focal length. And clearly, sort of half of D over F, well, the angle who's the arctan of that, the angle that's the tangent, that's going to be this angle phi here, which is half the field of view. So basically, the bottom line is the longer the focal length, the smaller the field of view. The bigger the imaging surface, the bigger the field of view. In fact, what's sometimes called medium format photography, instead of using tiny little sensors, they use much bigger sensors, so they can put still a lot of pixels but over a much bigger area. That gives them much wider fields of view.
Let's say you're at an art gallery. You've been staring at a painting that you really like, and now you want to take a picture of it. Your camera has a lens and a sensor inside. Now when clicking the picture, you obviously want the painting to be in focus. But say you also want it framed such that the picture takes up exactly the image area. That is, you want the width of the image when projected onto the sensor to match the sensor width. Let's assume that your camera lens has a fixed focal length of 50 millimeters. Your sensor width, denoted by D, is 35 millimeters, and the width of the painting, W, is 0.7 meters. Now with your knowledge about field of view, Can you figure out how far the lens needs to be from the painting and how far the image plane needs to be from the lens to capture the desired image in focus? Be mindful of units when calculating your answers. In order to solve this problem, first notice that we have two unknowns, z and z prime. What does that indicate? Well, we probably need two equations to solve. One is our by now familiar thin lens equation. That is 1 over z plus 1 over z prime equals 1 over f. Let us simplify this so that we can express one variable in terms of the other. Adding the two terms on the left-hand side and then cross-multiplying. Now say we want all the z's on one side. Take z common. And finally we can write z as z prime f over z prime minus f. Remember this last result. Now we need to think about a second equation. Look at the diagram again. See anything useful? How about these two similar triangles? They tell us that half of d over z prime is equal to half of w over z. Simplifying this, we can write that is z equals w over d times z prime. This is our second result. Remember we found earlier that z equals z prime f over z prime minus f. And now we saw that z equals w over d times z prime. Equating these two and solving further, we have z prime equals df by w plus f. Now put in the value of d, f, and w here. You should get z prime equals 52.5 millimeters. Putting that here should give you z equals 1.05 meters.
So here's something cool that's related to the mathematics of photography, which we'll do more of. And it's that zooming and moving are not the same thing, right? So some people think, oh, if I zoom in, it's just like getting closer to something. Well, it's not true. Here are two pictures of the same car, okay? And you can tell already that they look somehow different, even though it's the same car and the car is in the same place. And the reason that they're different is that on the left, the car was taken with a very large field of view. So that's a very small focal length. So that means the photographer had to get close to the car. Okay? The image on the right was taken with a small field of view, a larger focal length, so the photographer had to back away from the car. So even though that the car is the same size in the image, you'll notice right away that the shape seems quite different. All right? The one on the left seems to have a lot of what's called perspective distortion. And it's not really distortion at all. It's just the effect of perspective. And that's why I said we're going to do the mathematics of that. Really not today. We're going to do that in the next one. This has dramatic effects on taking pictures of people as well. So here is a example, again, taken from the web. The website in there says StephenEastwood.com, where it has tutorials on lens perspective. What we have here is pictures of the same woman, but over here it's a 350 millimeter lens, standing very far away, zoomed in. Here is a 19 millimeter lens, standing much closer in order to be able to get the same size face. And you'll notice that you get this incredible apparent change of the shape of her face. And over here that's referred to again as perspective distortion, but that's not really a correct word, it's just the effect of perspective. This is why photographers use particular lenses for portrait work, and they tend to pick a lens that lets them stand what they call a normal distance away. It turns out when you and I think about what a picture of somebody should look like, we tend to think of what it looks like standing somewhere around 6, 7, 8 feet away. Or maybe a little bit further, but certainly not closer. And that's why they pick the particular lenses that they do. Here's another example of what's called the effect of focal length on perspective, and here it's being called correct perspective effect. And this is a image out of the Zisserman and Hartley book. They're actually talking about the effect of perspective and weak perspective. We'll talk about that actually next lecture. But here are two pictures of the same building. Again, one taken with a much wider field of view lens, so the one on the left, so you see this effect as the object gets smaller away, and with a telephoto lens where the image on the right, you don't see any converging of the lines. And we'll talk about the mathematics of that next time. There's a really cool thing you can do about this, and that's something called a dolly zoom. And this was an effect that I think, at least I've been told, was invented by Alfred Hitchcock. Basically, if you move closer and closer to something, but you widen out the lens as you do the same at the same time, you'll cause the object and subject in the middle to sort of stay about the same size and to be stationary, but it's going to